Good day, everybody, and welcome to this fourth Conaperval International Conference. I'm Dr. Thierry Bernard, and I'm going to speak today about Blast Digital Twin for a sustainable mine. First, a few words about our company. We are a dedicated expert company that designs and supplies digital twin solutions for sustainable blasting and operating processes. And we do that for professional in mine quarries and construction industry. We've got people on the ground in various countries. You can see it on the screen. And today I'm going to speak about some digital tools, the digital twin for the mining industry. But first, let's look at the future of the mining industry. And if you look at the press, the magazine, or if you listen to mining conferences, you will notice these three keywords that characterize the future of mining. The first one is sustainable or green for the next mine. And this is going to be supported by digital technology and also automation and AI. If you look at the global chain, it starts from exploration, and then you've got marking, hauling, crushing, milling, processing. But if you look at blasting, that is the first link of the chain. Nobody speaks really about blasting, and consequently, if we look at the trends, there's no reason the trends will be the same for the blasting industry. It has to be sustainable and supported by digital technology and automation. If you look at blasting, the main goal of blasting is to crush the rock. But also we produce some vibration, noises, dust, fumes, sometimes fireworks, or sometimes we waste some ore body. And there's a big challenge if you look at blasting and sustainability. And one of the big challenges is the waste to value challenge. That means we have to get value about this waste effect. That is a big challenge, in fact. We're not going to really create value from that. We're going to minimize the loss of value. That is the consequence of vibration or whatever, firework or losing some ore body. To do that, we can use some digital tool, and one of the tools is the digital twin. So what is exactly a digital twin and a blast digital twin? A digital twin is something that is more than an emulation, or more, sorry, a simulation. It's an emulation. It's a digital replica of an object or a process, and it's connected to the real world. Connected to the real world for blasting means, for example, it's connecting to the drone to capture the terrain before and after blast. It's connected to the drills to capture the geology, and especially the UCS using the measurement while drilling, and also the whole location using the GPS. And it's, for example, connected also to many sensors such as seismograph or microphone, and can be captured after the blast to fragmentation monitoring system, for example, to assess the fragmentation. And the main idea is that the simulation tool, it becomes an emulation tool, because when it's connected to the real world, it adjusts itself permanently according to the flow of real data. So it gives the opportunity to do a lot of things, and we're going to see what we can do with that. The first things that you can do is, because it's based on physics, so the digital twin reacts to the changes of parameters in the real life. Here is an example of the digital twin running, and you've got on the top the emulation, and on the bottom view you've got the video. So when you play it again, you can see it's very, very similar. It's really duplicating what is happening on the real world. Even here, you're going to see there's some ejections that you're going to see here. If you look at closely on this simulation, you can see different type of rock sizes that simulate the fragmentation. So you get the small size and the mid size and the boulders, and when it's color coded, you have a better view. And if you have a close view on the video and you look at where are the boulders, you're going to see plus or minus the same thing. There it is. Then, if you look at on a larger window, here you can see on the side you've got a house, and if you run the emulation once again and you color code the ground vibration, you're going to see how the vibration they affect the house. And if you zoom on the model, you see also the movement on at the same time as you get the vibration. The idea is that you're going to use this simulation that is converted to emulation with the real data, and when it's really duplicating the real world, you've got the ability to manage some risk, some environmental or social risk, some environmental, but looking, for example, to biodiversity. We're going to see an example later on, or some geotechnical risk, like the big failure that you can have either on open pit or underground. And the idea is to move from risk to no risk, because you can anticipate what is going to happen. Because it's based on physics, it can deal with any type of configuration. So here you've got some different view, you've got tunneling, you've got a sub-level caving, you've got here some construction blast, cliff blasting, some gas blast here, or some iron ore control here. There's no real limitation of what you can do just because it's based on the physics. The main challenges that the blast digital twin solves. You get fragmentation, which is the main goal of the blast. Vibration, fly rock, cast. You get ore grade control, damage, and very important today, carbon footprint. We have seen that in the future of mining, we need to take care of sustainability. And taking care of sustainability, there's one big component today is the carbon footprint that we have to control or even more reduce. And with the digital twin, we're going to be able to deal with that also. But let's go have a look at a few examples, use case about this different topic that we can manage with the digital twin. The first one, for example, is fragmentation. If I come back to the emulation I showed you, you can see the mud pile with the different block sizes. You've got here the red one are the boulders, and the yellow and the green are the small particle size. And you've got also the distribution that is associated with that. Now, if you take an example like this one, where on the left side here, you've got the simulation that has been done. And then after the blast, when you add the final mud pile that is surveyed by a drone, and as soon as the drone finishes survey, push the result to the digital twin, that we can use it to either calibrate the digital twin, and in that case it's very well calibrated, you can see it. And if you zoom on it, you see how let's say close is the predicted mud pile or emulated mud pile versus the measured mud pile after the blast. You can even look at here where you've got some big boulders on the mud pile, and here you've got a range of boulder predicted also by the emulation. So as we get the fragmentation, as soon as the digital twin is calibrated, then any configuration will predict the fragmentation and help us to manage it. So then either you can use it as a predictive tool to do the optimization. So if you're not happy with the result, you can change the parameters in order to get a result that is acceptable for you. Here we come back to the first video, and we're dealing with complex geology. Just to show you here this ejection that you have seen here on the video, and if you look at here, you're gonna see the ejection here and here. The emulation really replicate the real world because the drilling machine can report in real time that here at the bottom you've got a layer of clay. It is a soft rock, and the measurement work drilling reported very low UCS. So when it's incorporated into the model, you can see that here you've got the ejections, and this clay that is here, it's basically clay that is in brown. You see the brown particles flowing. Of course, there's some rock around is flying too, but that's why you've got this accurate prediction, just because the measurement while drilling reported the real work of the rock strength. Now, this is another example with about vibration. That is an example that is based in Brazil with Vale company. And you know that in 2019, there is a significant accident where you have a dam that collapsed, and it was a big accident. There were people killed, and also some huge environmental effects with this tailing dam collapsing. And the blasting operation was stopped for more than 1 year, 62 years. And then to restart the operation, they have some constraints about the dams around the pit. And you get the pit here, and there is some high level of constraints, and sometimes lower than 1 second. And it's close to the pit. This is typical view of the dam. It's earth dam with some seismic sensor or piezoelectric sensors. But there's also some caves in the pit area, and the caves are some environmental structures where that the mine has to protect, and there's plenty of caves in that pit, for example. There's a typical view of what is a cave with some biodiversity inside, and there is some sensors, in that case seismic sensors, to check that the vibration are not too high according to the local standards. And now if you have a global view of a typical mine blast here, you get a cave here, very close to the blast, and you get the dam in the background, and you have to control the vibration on both. If you use the digital twin, you calibrate it on site, and when it's calibrated, you've got something like that where you can see the movement simulation that show you that the model is well calibrated with the real data, the field data. And then you can use the model to predict the vibration on site. And here you see the vibration radiating around the blast, propagating in the environment. So you can see the impact either on the caves or after on the dam on a larger scale. And this is, for example, here on much larger scale. So you can see some. So we've got a tool to predict the vibration before the blast happens, and we can also prove that you can have the vibration under control on all the areas. Finally, if you look at the end of the simulation, you've got the vibration on the cave here and on the dam, and you can check that the vibration are in line with what you expected. And because the system is predicting, it's really duplicating the real world. It's also predicting the full waveform of the vibration everywhere, so you can check the frequency and everything. Finally, it helps a valley to resume the blasting operation close to the tailing dam. And this is what the user, the client says they were happy to use this digital twin to restart their operation. Okay, there's another use case where you can, we're going to look at the ore grade control. So ore grade control is a key thing in the mining industry. We have to recover the ore and recover as much as we can. In this example, you've got a video of the blast, and on the right side, you've got the emulation of the blast that has been calibrated in that case. And the ore body is color-coded with the ore grade. This is iron ore. And then when it's color-coded, when it's calibrated, sorry, like this, and you see that the result, that the final mud pile is very close to the real one. Then you can start doing optimization about ore grade control. So the principle that was used here for that mine is to explore 3 scenarios. Basically, in that case, they use the same timing. You see the timing is color-coded, so you see initiation, it's a V shape, and it's progressing around the V shape. But they decided to check different patterns. So here you've got a 6x5 and 1 meter as a stemming, 6x5 with 1.5 meter and a 5x4. And also different diameters. So 3 different scenarios. And the idea is to say, okay, let's use the digital twin and let's check what are the results in the 3 different scenarios. So for each scenario, you're going to predict the movement. And if you superimpose the block model, that's the case here, you see the displacement if you do a cross-section of the mud pile. And you've got also the fragmentation here, fragmentation distribution, when you do it for scenario number 2 and for scenario number 3. So 3 different scenarios, 3 different results. You can see here that the movement is very different from scenario to scenario, even if the timing is the same. So depending on the pattern, and then also they can check the fragmentation. So at the same time, they've got a view of the movement and what is going to be the more suitable for them. And they've got also a view of the fragmentation that is depending on the pattern. You can also have a look of the damage, the back break. And here you see there's a different back break on the different scenarios. So you have the movement that will create the dilution and the fragmentation and also the back break. And you can also add the carbon footprint. That was not done at that time, but we did it later on just to see the different impact of the carbon footprint. So at the end of the day, you've got 3 simulation based on calibrated digital twin, and then you can select the one that is the more compatible with what you're looking for. In that case, what was done is that there was some economics that were done for each scenario. Let's say looking how much ore we can collect depending on the movement, and also with a ratio based on the cost that is based on the pattern. So it's changing the powder factor and the drilling cost. So you've got the baseline, that is the standard blast that they used to do, and then you get the three different scenarios, and for each there's a calculation about the overburden, or the low grade for the ore that is recovered, the ore, and the value in dollars. So then you can draw some graph like this with the different scenarios. And so here you've got the value, and here you've got the volume you can collect. And what is interesting is that you've got if you look at here, you've got more value where here you've got the more value, but here you've got the more volume. So here you believe you're recovering more, you believe in you're recovering more ore because you recover more rock. But in fact, due to the dilution and the movement, you will certainly get a better result here, more value with a small volume, but let's say with more high level of grade. And you can also add the carbon footprint on top. If you add the carbon footprint on top, then you have a view of the impact. So you see here, that's the little impact, the less impact on the carbon footprint, but it's not the highest value. The highest value, you put a higher carbon footprint in that case. So at the end of the day, you can really deal with that, and the digital twin helps you to do some prediction and to manage that. So we can conclude by saying that we can win the sustainable challenge in blasting, try to make blasting sustainable. We use a digital twin. We've got 4D emulation that show you the movement, the fragmentation, and the vibration, and then you can manage your risk. Try to move from no risk to no risk, because you can anticipate everything, and if something change versus what was planned, you can adjust it. Like, imagine that your drill is not going to drill at the right place because the rock is not what you're expecting, is not that competent. The digital twin will automatically adjust the simulation and the emulation, and you can see the impact. This is another view of what we can do with the digital twin. Here, we're using the digital twin to see what is happening with the trucks and the heavy equipment on site, and especially as regard the noises or the carbon footprint. So it also helps to control these kind of things, depending of the movement of the equipment and different slope and how are loaded the trucks. You've got a different view of the impact, either of could be the noise, or it could be the carbon footprint if you just change the scale, and it's really showing you how it impact on the pit. I hope I could give you a good feel of this new digital technology, the Blast Digital Twin, and how it can help for sustainability. Once again, can help for the environmental impact, basically the vibration and the air blast, and either on the houses or on the biodiversity. It can really help to maximize the recovery of our grid, and here we are really addressing the waste to value change. Carbon footprint, decarbonization with improving the fragmentation, because the fragmentation is what uses the most energy if you do fragmentation in the crushing or the milling plant. So if you can improve the fragmentation by blasting, you're going to really improve your carbon footprint. And also all the risk management, especially on the geotechnical failure, either in open pit or underground. And I would like just to finish to thank the Conferencia team to give me the opportunity to present you this new technology as regards the future of mining, and thanks all of you for your attention. So now I'm going to be available for a few questions. Thank you.